Hey class, this is going to be your 7.9 lecture, which is your final lecture for differential equations. So what we're going to do here is we're going to solve a non-homogeneous linear system. So instead of it just being x prime equals ax, we have a driver function g of t. If you think back to how we did this in chapters 2 and 3 for the regular linear equations, very similar. First, we solve the homogeneous case to get xc. All right, xc is going to be some combination c1 x1 of t plus c2 x2 of t, and here we're going to say x1 and x2 form a fundamental set of solutions. At this point, we need to find one particular solution xp to, let's go ahead and call that guy star. We're going to use him a bunch. To star. X equals xc plus xp is the general solution to star. This step right here needs a little bit of expanding on, though. There is a method in your book on around page 432 to 434. Could be off by plus or minus 1 pages here because we have different editions of the book, where you diagonalize the matrix. I'm not going to cover that. We could also, so this method is called diagonalizing. I mean, that's at least a step in it. We could do undetermined coefficients. That would also work. We're going to get quite a system of coefficients for that typically, though. And so the method I'm going to show you is variation of parameters. And lastly, we could also use Laplace transforms. You can find this in your book too, page 438 to 9, again, plus or minus 1. Maybe 2 by this point, I'm not sure. If we were together in class, I'd probably show you an example of this, maybe on Thursday's class. But I think I'm going to focus just on teaching you this one method, which works a good chunk of the time. Of course, the problem with variation of parameters is sometimes you end up in a situation where those integrals that you need to do are difficult. But otherwise, it's a nice general method that works most of the time. So, what do we need for variation of parameters? For variation of parameters, we need, I'm not going to call this psi, I'm going to call it f. F of t is a fundamental matrix for the homogeneous case, x prime equals a x. In other words, f of t equals x1, x2 in either order. So find your solutions. I mean, technically this works if this is higher order than 2, but for our typical case, A was a 2 by 2 matrix. So in that case, we find any two solutions that make a form a fundamental set of solutions, and we put them in our matrix, our fundamental matrix. In that case, so we've got our complementary solution kind of embedded in that. We get variation of parameters tells us that xp of t is going to be f of t times the integral from, this is from t naught, which would be the value of your initial condition should you have an initial value problem here, up to t of f inverse of s times g of s ds. All right, so I didn't mention this up above, but once we have a fundamental matrix, the next thing we're probably going to want to do is invert it. We're going to want to find f inverse of t. So let's work an example. That's the method. Here's an example. Given that f of t equals, we're going to start with our fundamental matrix here, t plus 1, 1, t, 1 is a fundamental matrix on 0 to infinity for x prime equals 1, 1, negative 1, negative 1, x. Use variation of parameters to find the general solution of x prime equals, same matrix, otherwise this doesn't work, times x plus the driver function 1 over t, 1 over t. So we can start pretty simply by saying, well, what is xc? Might as well just talk about it. So xc of t is equal to c1 times the vector t plus 1t plus c2 times the vector 1, 1. We just took our columns of f and remembered that they formed a fundamental set of solutions, so we took a linear combination of those. Now, we're going to want to find xp. So we have f of t equals t plus 1, 1, t, 1. So now we need to find f inverse. F inverse of t is 1 over the determinant of f times, we need to switch these guys and negate these guys. And the determinant of f is t plus 1 minus t, so this is just 1. So f inverse of t is just 1, negative t, t plus 1. Now we use our variation of parameters formula. Xp of t equals f of t times the integral from t0 up to t of f inverse of s times g of s ds. And in this particular case, that is t plus 1, 1, t, 1, the integral from, let's see, looking through here, we can't start it at 0. 0 doesn't work because we've got stuff like 1 over t. Let's go ahead and start this guy at 1. Up to t of f inverse, but of s, so that is 1, negative s, s plus 1, g, but of s, so it's times 1 over s, ds. Same integral, except we're going to go ahead and do that multiplication real quick. So we get 1 over s minus 1 over s. The top number is 0. The bottom number, we have negative 1 plus 1 and then plus 1 over s. So we get 1 over s ds. This is just down off the bottom of the page. Sorry about that. That was 1 over s there. This is just 2 basic Calc 1 integrals. So this is t plus 1, 1, t, 1. The integral of 0 is just going to be a constant, right? And then a constant evaluated between t and 1 is going to be 0 again. And then the integral of 1 over s is going to be the natural log of t minus the natural log of 1. That was the good reason to start this at 1. So we end up with the natural log of t. Now we can multiply that out. We're going to get the natural log of t. We're going to get t times 0. We're going to get the natural log of t again. Maybe you don't like it written that way. Maybe you'd rather write it this way. It's totally up to you. So that's xp. Previous page, let me pull it up real quick, remind ourselves what xc was. We can see it now. So x, our solution, as a function of t, is going to be c1, t plus 1, t, plus c2, 1, 1, plus the natural log of t times 1, 1. That's our xp. So that is variation of parameters. I mean, the nice thing here, we already had a fundamental matrix. But that's really all there is to it. Good luck. Let me know if you have any questions.